This session, we're going to discuss how integers is being represented. So we have different ways. So we have different ways to represent integers. So we have octal, hexadecimal, we have binary, and others. And also the well-known, which is base 10. Okay, those are the different representation of an integer. And we're just going to discuss somehow the base conversion algorithm and algorithm for integers operation. But we already discussed this in your other courses, so we don't need to discuss it further. Okay? So in representing integers, so basically we represent it usually using decimal or base 10, wherein each positional value is based on 10 notation. Okay, so for example, we have 965. So the positional value of 5 is 10 raised to 0. For 6, it's 10 raised to 1. 9 is 10 raised squared. So this is your ones, tens, and hundreds. And also, nowadays, we use base 2, base 8, and base 16. So most of the time, we use this in computers and in communication. Okay? So to represent our data. So aside from base 2, base 8, and base 16, and base 10, we have other number system or base number to represent our numbers. Okay, so in Papua New Guinea, they have lots of counting system. So at least 900, okay, different counting system. So they use their body, usually they use their body to represent numbers. So for example, they use their hands, their two hands, and their 2 feet. So the first two hands rather represent 10, okay, 1 to 10. And then for the feet, so it will represent 11 to 20. So they use base 20 system to represent an integer. Okay, so for example, if we are talking about 15, so it will be represented by 2 hands and a foot. Okay, so it means 2 hands means 10 and 1 foot is 5. So if we're referring to 20, we're talking about a man, not 2 hands, not 2 feet. Okay, but a man. Aside from base 20, some of the Papua New Guinea tribes use more body parts. So in this example, in this picture, they represent I. I is used to represent 13 and 15, and their nose used to represent 14. Okay, and their this it is represented by 11 and 17. Okay, so based on this, they use base 27. Okay, so if it's more than 27, it will be represented by a man. So if we have 40, so a man, and so we need 13 more. So which body part represents 13? It's the right eye. So a man and the right eye represents 40. So that's another, okay, representation of our integer. And again, this is used by Fayol tribe in Papua New Guinea. And in Babylonian, we use the segments of our fingers. So it will be 1, 2, 3 up to 12. And the right hand, the right hand represent 12, 24, 36, 48, 60. So basically, Babylonian use base 60. Okay, so that's why they invented minute seconds. Okay, based on 60, based on 60. Okay, and for representation, okay, so for writing, so they use this symbol. So for 1, this is the symbol. So 1 to 9, it means 9 of this. Okay, in case we have 10, so it will be on its side. Okay, so this will be the symbol. So 10, 20, 30, 40, 50. Okay, so the number of this will determine the number of how many, okay, 10 that we have. But in case we have 60, it will go back to this symbol. Okay, so it means 60. So it means Babylonian use base 60, okay, in this representation. Okay, so for example, so we have 61 upright, and then we have the on its side 1, 2, 3. It means 30, and 9 of this it means 9. So we add 60, 39. So we have 99. So that's how we represent numbers, okay, in Babylonian in writing. Okay, and this is how Egyptian number is written. So it is base 10 actually. So this is the symbol for 1, for 10, for 100, for 1,000, for 10,000, 100,000, and a million. So number of this will determine the number of 1,000, the number of 100s, and others. Okay, so for example, we have 1,996. So it means how many 1,000 do we have? We have 1. So that's why we have one symbol for 1,000. And for the hundreds, how many hundreds do we have? We have 9. So that's why we have 9, 9 symbol for 100. And for the tens, how many? We have 9. So that's why we have 9 here. And for the 1, how many? 6. So we have 6. So this is the representation of 1,996 in Egypt, ancient Egypt. Okay, and this is the complete list of the Babylonian numerical numbers. So in base 60. Okay, and then in Mayan we use dash and this symbol of cocoa bean to represent 1, 2, 3, 4, and a 5. Okay, so if it's 5, so we're just going to use a dash, a line. So what does it, so for example, what does it mean? So 1, 2, 3, it means 15, and 3 means, so we have 18. Okay, so that's the meaning of it. Okay, so in Mayan, they use base 20. So this is the complete symbol for each numerical value. So this is the symbol for 0, and the rest for 0 to 19. Okay? And for Roman numbers, so you're familiar with this, it was been discussed during our elementary days, or probably in kindergarten days. So we use letters to represent numbers. So V for 5, X for 10, L for 50, C for 100, D for 500, and M for 1000. And for 1, we have I. Okay. And for Indian, so they use base 10 and they only have 10 symbols. So from 300 BC up to the 16th century, the symbol changed, okay, evolved, and the evolved symbol was basically the new symbol for the base 10. Okay, and also in Indian, or the Indian is the one that invented zero. They are the one that they are the one that introduced zero or empty value or no value. Okay? So from this symbol up to this symbol, as you can see here again, now it somehow near to the modern representation of our numbers. Okay? And other bases we have, again, we have base 8, base 10, base 12, base 20. So base 10 is decimal, we all know that. Base 20, so we call it vigesimal. And base 8, octal, which we know. And base 12, duodecimal. Okay? And then base 60, sexagesimal. And some no special names such as base 5 and other that chooses body parts to count. Okay? And again, for base B representation, we use positional notation to determine the value, okay? How big the number is, okay? So the first position on the right side, or on the left side of the radix point, or the point, will have exponent. The base has an exponent of 0. Then from right to left, it increases by 1. So that's the logic behind the positional value of a number. Okay, so binary expansion. So again, integers could be represented by binary. Okay, so this is an example of a binary. So it only uses 0 and 1 to represent our numbers. Okay, and just to differentiate binary numbers with the other number system, we use a subscript. So subscript 2 means it's under binary. Okay, I'm not going to discuss how to convert binary to decimal since there is a video lecture in Logic Circuit. So kindly refer to that video lecture. Okay, so if you want to determine the position, the equivalent of the binary integer or binary number in decimal. Okay, so we're just going to multiply each digit by its positional value and then add, and that's the equivalent in decimal. Okay, so that's the logic behind the conversion. And for the octal, same. Okay, so for the octal, base 8, so the symbol to be used is 0 to 7. We want to convert, so same solution, same process. Just multiply each digit by its position value, then add. And for the hexadecimal, since our integer or our numerical symbol is limited to 10, so we need to have 6 more. So that's why we use letters from A to F to represent 10 to 15. Okay, so if we have 2 A, E, O, B, 1 E, 5, okay, so we want to determine the equivalent of it in decimal. So again, just multiply each digit by its positional value. B is 11, E is 14, A is 10. So after multiplying, get the sum, and that's the equivalent. And for 1E5, this is the equation, and this is the solution. Again, E is 14. So multiply each position value to its corresponding digit, and then get the sum. That will be the equivalent in decimal. Okay, so that's the rule from any base to decimal. Again, complete discussion of this, kindly refer to the logic conversion video lecture. Okay, so just going to, I'm not going to discuss this since we're taking up logic circuit now. So you know this, you already viewed the video lecture about it. Okay, so just a comparison of octal and binary, okay, and decimal. Okay, so that's how we represent from 0 to 550. Okay, so that's it for how we represent integers using any base. Okay, so for the next video lecture, we're going to discuss primes and greatest common divisor. How primes can be used to define the GCD of certain numbers. Okay, so thank you. So see you on the next video lecture.